Well, I will start with, well, distinguished ladies and gentlemen. First, I would like to welcome you all to the first online seminar of the Low Latitude Ionospheric Research Working Group of the Regional Advisory Committee of the Asia-Oceania Geoscience Society. Before we begin this seminar, I would like to express my heartfelt gratitude to all of you who sincerely committed to this event to make it a success. This event would have been impossible without the support of each and everybody present here. I would like also to thank very much to Dr. Wing Huang IP for all his great efforts and for giving me the opportunity to chair this seminar. Nowadays, the ionosphere is becoming very important to human life, and the available measurement data, especially in altitude, is insufficient for practical applications such as positioning, navigation, and radio communications. As you know, GNS radio occultation can observe ionosphere globally and can provide vertical profiles, as for example, the Formosat cosmic missions. GNS radio occultation ionosphere sounding can provide thousands of vertical observations per day, and the 3D structure of the ionosphere can be reconstructed with several weeks of data. Then, with this large amount of radio occultation observations, is it possible to reconstruct the global structure of the ionosphere in 3 dimensions. This provides us the opportunity to investigate the vertical structures such as disturbances due to geomagnetic storms or solar eclipses, plasma depletions, earthquakes, and tsunami anomalies, and many other events. This talk is given by Dr. Chi-Yen Lin, an assistant research fellow at the Center for Astronautical Physics and Engineering in the National Central University in Taiwan. Dr. Chen-Yen Lin received his doctoral degree at the National Central University in 2015. During his PhD, he visited the Cooperative Institute for Research in Environmental Sciences at the University of Colorado Boulder and the Space Weather Prediction Center at the National Oceanic and Atmospheric Administration in the US. His research interests cover GNS ground-based and radio occultation for ionospheric observation and analysis, machine learning, ionospheric space weather, ionospheric reconstruction, modeling, and ionospheric data assimilation. Ladies and gentlemen, with the attendance of experts and people from different backgrounds, more beneficial ideas and experiences can be shared in this seminar. I look forward to seeing a positive outcome from this event. Thank you very much. And thank you very much, Dr. Chi-Yen Lin, for giving us the pleasure to see the impact of radio occultation observation on space weather monitoring and research. Dr. Chi-Yen Lin, please proceed.
Okay, thank you.
Yes, we can say it.
Okay, so I'm Jenny, and the seminar talk is the impact of radio occultation observation on the space weather monitoring and research. So in this talk, I will introduce how the radio occultation influences us. Before, we only have the ground observation, but now we have the more space measurement and like radio occultation, and it impacts the research and also space weather monitoring a lot. So like before, like we only have the ground observation like radar and ionosound, and now it's digisound data, and we can receive the continuity peak ionosphere peak density NF2 and the peak high HM2, and when we have the GNSS satellite, for example, like GPS, and we can use the ground-based receiver to receive the GPS signal, use the dual frequency to calculate the total electron content along the satellite signal path. And this figure just shows the ground-based receiver in the North Taiwan is a one-day observation. and each different color line shows the one GPS satellite observation for this vertical TC, so we can use the we can transfer from the stand TC to a vertical to gather horizontal information. And this figure shows the global and the ground-based receiver in the IGS database. There's more than 2,000 receiver in the database, and the blue triangle it shows the receiver location, and the gray line it shows the coverage of the observation. Like each for now is most of the observation can receive GPS, GLONASS, Galileo, and Beidou, and even more GPS GNSS receiver, GPS satellite, and but we have more than 2,000 observation receiver. But you can see at the Pacific Ocean, at Atlantic Ocean, and also the Indian Ocean, there's not much observation because most of receiver is on the continental and the island. So we have lot of places we don't have the observation. So even we have the continuity observation, but we still don't have much data for the global. So like scientists doing like a spherical harmonic use like 200 or 200 to 300 observation receiver to use a spherical harmonic to reconstruct the ionosphere TC map, the so-called global ionospheric maps, GIN, and a lot of instruments to produce this map, like code and JPL, or like ESA, and like Wuhan University, and also like Taiwan, we have our own GIN. And this one you can do more observation, but that has a problem because if the place we don't have the GPS data, like maybe like ocean, and like a Pacific Ocean, or like Atlantic Ocean, if they have some signature, we cannot guarantee it's true. Maybe it's just for the spherical harmonic. So this is a problem that maybe we need to solve because we don't have data. And in the 2006, we have the Formula 3 Cosmic. It included 6 microsatellite, and we can use a radio occultation, and we can have about 2,000. I think the maximum is 3,000 radio occultation per day, and every 1 hour is just like 100 to 150 radio occultation. And this figure shows the coverage for the radio occultation, and for Cosmic 1, and the blue dot shows the radio occultation location, and the triangle shows the GPS station. And for radio occultation, it's not only important because for we can observe like on the sea, and on the ocean, and on the continental. But the more important thing is this observation geometry. For before we can show this, we can see this geometry. For before we use, or if we don't have the ground-based receiver, like we can receive the GPS GNSS signal on the ground, and we can observe the ionosphere horizontally, so we can gather vertical information for the ionosphere. But the radio occultation data is different. We can have you can see the black line. It observes the ionosphere horizontally at different altitude, so we can gather vertical information. So it's a total different. Like for the ground-based receiver, it provides horizontal information, but for the space-based measurement like radio occultation data, it provides vertical information for the ionosphere. Okay, sorry. And this one shows like how we gather electron density profile, because we did not when people see the radio occultation electron density profile, it do a lot of things. For us, like when we receive the GPS signal and doing the aberrant we calculate the TC and doing the aberrant inversion to gather electron density. So what we got is like for example, show this geometry, like when a LEO satellite at the B location, and we can receive the GPS at the A location. Then we use the dual frequency, so we can gather TC from the A to B, like TCAB, and then this we call the occultation site TC profile, is because from here to here. And so there has a vertical profile, and when we like in the C location, and from the top satellite altitude to the C location, from here to here, we can gather TC from the A to C, between A to C. We call the accessory site TC profile. And we divide TCAB and the TCAC, then we can gather cabinet TC is TC from between the B and the C. So we can the cabinet TC means like the TC only impact in the ionosphere, not the plasma sphere. And then we do the aberrant inversion. The aberrant inversion is like first we assume the electron density at the satellite orbit's altitude, and we assume this the electron density, and then to the next observation, the TC something pass, and because for here and here we already assume, because when we do the aberrant inversion, we need to assume the ionosphere is a spherical symmetry. So for same altitude, the density is the same, and for here and here we assume the density, and we can divide the TC here to here, and we can get a tangent point location, the electron density at here, and to the next altitude TC, and we already assume the density here and here, and we also gather electron density here and here and here is the same. So we can divide this TC and this TC, then we can gather 10 the electron density at this tangent point, and go on, then we can gather electron density profile. So for the radio occultation, the electron density is from the top we infer from top to down, and use the TC profile to electron density profile. And so when we gather a lot of electron density profile, and how we can do like this study is for Professor Charles Lin in 2009. He used the monthly cosmic electron density profile to accumulate a month's data, and to see the Whittlesey anomaly, three-dimensional anomaly structure. And before, maybe we can just use like the Iono song, or like a few radar station to see the three-dimensional structure. Maybe just a two-dimensional is because just for the altitude information. But when we have the cosmic data, the radio occultation data, we can use for the three-dimensional. We can see the three-dimensional structure in the ionosphere. And this study is from the Dr. Fuyan Zhang, is in the 2020. It's used the cosmic data to see the plasma depression bay in the equatorial ionosphere. And this one shows in the October into the Mars at the 275 kilometer altitude. There's a depression. There's a plasma depression around the East Pacific Ocean, but moved to the April to September, that the depression has changed. There has different depression bay and at the Atlantic Ocean and in India and also the west Pacific Ocean. And before, if we don't have the radio occultation data, it's hard to do it. And this one is a very interesting study, like use radio occultation data. Like after the Nepal earthquake, it's a tragedy for the earthquake, but when we see the radio occultation data, there has only one because it's 2015, almost 10 years after the cosmic launch, and we only have the one microsatellite, and but it's it's hard to say lucky because it's earthquake, but we got a three reaction density profile around after the earthquake. There has a we found that it has a significant uplift for the red profile, and but another two like black and gray did not have the uplift. And we checked the location and found the red profile received the radio wave influence faster than the two. And when we get the radio occultation profile for this black and gray profile, they did not influence by the earthquake. So we can see there's a significant uplift for the ionosphere there about 330 kilometer altitude. And for another case is tsunami. The tsunami, like after Tohoku earthquake in the 2011, we found that it has the profile that has a disturbance just in north the just north the apex center, and the south did not, and it is for the disturbance is influenced by the tsunami. Okay, sorry. And but for the radio occultation, it's not perfect, because before when we told how we get the electron density profile, we assume the ionosphere is a spherical symmetry, but actually we know the ionosphere is not. So it has a bias for the Albert inversion, because we assume the ionosphere is the spherical symmetry. And this one is Professor Tiger Liu in the 2010 that we do a simulation for we got a simulation choose from the international reference international reference ionosphere, and we got a TC profile from the IRI, and do the Albert inversion, and we found it has a significant bias or error in below the 200 kilometers. Because that is because the spherical symmetry assumption. And we try to do a different things, like Dr. Mingyang Zhou in the 2017. He used the previous monthly three-dimensional reaction density from the radio occultation to gather three-dimensional structure information, and to calculate the spherical asymmetry factor, and then use the spherical asymmetry factor into the Albert inversion. And we can see the simulation result shows that if we just use a standard Albert, below the 200 kilometer, we can see the significant plot the cave structure is due to the spherical symmetry assumption. But if we added a three-dimensional asymmetry factor into the Albert inversion, we can see it reduced the impact from the spherical symmetry. and we call this one is NEAD-RBEL. And you can download this product in the TACC CWB. Is called the IGA profile. And but after before that, we also try to do another way, like before, just I say, like a ground-based GPS provide a lot of horizontal information for the atmosphere, and the radio occultation data provide a lot of vertical information. Why we not try to combine these two kind of data to get a better atmosphere? So we try to use a data assimilation way. We call this one is a global atmosphere specification. And in this data assimilation approach, we use a common filter. And the background is used II 2016. And we assimilate the ground-based GLSS length TEC, and also the Formosa 3 cosmic radio occultation length TEC, not electron density profile. And for now we assimilate the Formosa 7 cosmic 2 radio occultation length TEC. And we try to create like the 3-dimensional electron density for every hour, and for the resolution is 5 degrees for longitude, 2.5 degrees for latitude, and altitude is 20 kilometers. And this one is show the example. Okay. It show the movie like example for the one day, 24 hour. You can see the 3-dimensional electron density structure. Like west move to the, and you can see at each different longitude, you can see the vertical structure, and also we can see the horizontal structure at different altitude. And how we do is use a common filter. That in our common filter, we have the measurement update and the forecast day. And in the measurement update, we calculate a common gain, and assimilate the data in the innovation part. Y means the observation, HX means the background, and we use a common gain to decide which one is, well, this observation is influenced a lot or not. And we also update the model error covariance. And to the next time state, and we forward forecast the electron density by previous time state, like and then to the next, and to the measurement update state, we use the forecast state electron density and the covariance to assimilate the observation again, and also update the covariance. So it's like each time state we have the forecast state and the measurement state. Like we assimilate each time, every time state to make a better atmosphere structure. And this one is because because the IRI is an empirical model, it's hard to do the forecast. So we try to do another way, like we shift the electron density along the westward, shift 15 degrees along the geomagnetic coordinate. Like by every hour we shift 15 degrees, and this one is before the shift, and at 400 kilometers and at 300 kilometers. And after the shift, and you can along the geomagnetic coordinate, and the electron density is westward shift 15 degrees. And this one is show the simulation result. It shows simulation result if it's a simulation choose, and the background they have come from different model, choose from the symmetry, and the background is II. And then we can see the structure is this one is for the A hour, is after the A time state. So we can see for the choose the structure, for the is the Willow-C anomaly structure is very different to the II. But after the A hours data simulation, you can see the structure is much more close to truth than the background. it means, and not only the width anomaly, and you can also see the EI cross is much more close to truth. So it means that the estimation works very well. And this one shows the Rubin square, and the red line shows the difference between the truth and the background, and the blue dashed line shows if we just assimilate the data without the forecast state. That means that every time state we start from the background, so we can see the Rubin square error is much more close to the truth. So much more close to the background. And if we added the forecast state, you can see that after like 8 to 10 hours, the error becomes stable and much more not like the dashed line is still based on the background. It is far away to the inference from the background. Sorry, and we also do the validation with the GIN, and we can see the data estimate result is the structure is much more is close to the GIN, even like this structure. Even when I see the structure, I see, oh, okay, this EI is works not good, but when I see the code result, okay, they look similar. And we also validate the GPS vertical TEC. The blue line shows the difference between the GIS and the vertical TEC, and the red dot shows the difference between the code and the vertical TEC, and you can see their structure is well agreed. And we also validate with the INSON for the NF2 and the HM2 just for the three station, and they show the structure is well agreed. And after that, for now, is the Formula 3 Cosmic is already done. The mission is successful done, and for now it's Formula 7 Cosmic 2. It launched in 2019, and because the incorporation is 24 degrees, so the coverage is within the, for the radio occultation is within the 40 degree latitude. But we have much more data because for Formula 3 Cosmic only receive the GPS signal, but the Cosmic 2 we not only receive a GPS signal but also a GLONASS signal. So we get a much more data than before. For now, I think it's 5,000 radio occultation for ionosphere per day. And this one shows the GIS, the albedo inversion, like a standard electron density profile, ion profile. It shows at the 13 October 2019, 10 UT. And this one shows the IGA profile we call the NE80 albedo at the same time. And this one shows the GIS at the same time for the horizontal or the vertical structure. And you can see, even we have much more observation, but it's hard to see the structure, what the ionosphere looks like. But if we see the GIS, you can see, oh, there has the EI cross has two crusts. And also you can see a clearly horizontal structure. And also we compare our GIS with the monthly albedo and the monthly NE80 albedo, and you can see the standard albedo inversions, albedo electron density profile. That has a two artificial cave structure below the EI crust. And for the NE80 albedo, because we added the spherical symmetry, a symmetry factor into the albedo inversion, so you can see the artificial cave is not like a standard albedo division so deep, but it still has a little plasma cave structure. But because the GIS only use the common filter, we do not assume the ionosphere is a spherical symmetry, so we don't have the problem for the plasma cave structure. And this one is show the different time state, and then we can see that has the structure for this, the monthly structure is similar to each other, except below the 200 kilometers. And this one is shows the stone signature. This one shows the stone signature, and we can see at September 28, 0 UT, there's the mean phase and the recovering phase. So during the mean phase, we can see the electron density, the EIA crust become larger, and the fabric become larger, and we can also see the RBL and the NEA RBL that has a electron density enhanced. And during the mean phase, we can see the EIA crust become just a one crust, but because for 1 hour RBL and the NEA RBL, we cannot see the whole structure. Yeah, so if we want to see like a dramatic stone signature, the GIS has a better performance to see how the ionosphere change influenced by the dramatic stone. And now because we also validate with the digital station, and we use the manual square and for the 2 months, and we compare the NF2 and the HF2, and we can see we also do the RBL and NRBL to compare with the digital, and we can see the correlation between the RBL and the NRBL to the digital observation is 0.88. It's very high, and for the GIS for NF2 is 0.8, and for HM2 is 0.778. It's a little lower than the RBL and the RBL. But if we just consider the point, if the GIS will when the digital location has a radio occultation at the same time, and we can find the correlation, it becomes 0.9 and 0.86. It means that like if we have the radio occultation for GIS, we can get a better performance. And this one is show how if we have the GIS, how we can do. This one is the Dr. Rajesh study in the 2021, and it shows that has the minor that has an extremely positive ionosphere storm triggered by a minor geomagnetic storm. Because the geomagnetic storm, I think the DST just like minus 60, but they have density is enhanced about at 200 to 300 kilometers, enhanced by the 300%, and it's very unique. And another one is shown by the Dr. Jatin Lin study in the 2019. There's use the day-to-day availability of the SW2 amplitude during the 2009 SSW. And before, if we just use a cosmic data, we need to use a 20-day to combine the three-dimensional structure. So you can see when the density enhanced, there's NF2 reduced and then enhanced. But if we use the GIS, it's just, we just need we don't need to accumulate any data. We just every hours, and we can find that when the enhance that when the temperature enhanced, there's NF2 reduced and then enhanced, and after that it has again to reduce and reduce after that enhance again. But if we accumulate that 20-day, because it becomes like smooth, so it is hard to find after one enhance, it has a second enhance. Okay, for the conclusion, it's like radio occultation sounding provides a lot of vertical observation in the ionosphere worldwide, and radio occultation sounding can provide observe the large scale like EI cross, and also like a small scale disturbance like induced by the tsunami or like earthquake radio wave signature in the ionosphere. And the GIS, the data simulation model, considers a common filter by assimilating the ground and space-based observation, can reconstruct the three-dimensional continuity ionosphere electron density structure. And RBL electron density profile and the GIS capture a similar cosmology structure of the ionosphere in the longitude and the latitude structure, like longitude is for the waveform structure and the latitude is for the EIA crust. And RBL electron density profile detects the response to a geomagnetic storm, but the GIS performs a better reconstruction in the EIA crust variation. Okay, so that's my conclusion. So if you want to download the GIS, the GIS now is operational. You can download in the TACC CWB. There's a GIS link. You can download every day, every hour, three-dimensional electron density structure, and also you can download it in the NCKU, the website here. Okay, that's my presentation. Thank you.
Thank you very much, Dr. Lin. It is an amazing work you have been done with the ionosphere. I think is very important for the research community, increasing the measurement data and assimilating with the model, so we can understand much better and to characterize the small structures such plasma bubbles and how they say in short time. So we have more measurements. Yes. We have higher resolution in time and higher resolution in space in 3D, so we can also study the coupling with another variables such thermospheric mass density, which is the one I'm studying. And well, I will give the time for questions. If somebody want to make a question or some suggestions to Dr. Lin about his job, yes, please. I think some, yes, Haisha, Dr. Liu.
Hi, Dr. Lin. Yeah, very interesting work and excellent. I see the very good reconstruction with the data simulation, especially adding the R data. I have a question. Could you go back to the slide 29?
29, okay.
Yeah, the correlation one. Yeah.
Yes.
Yeah. It's strange for me. The subplot B. The yeah. It seems that the correlation is the number is the same for the subplots, right? It's a 0.885.
Yeah, the correlation is a little higher than the RBL inversion to the digizone. Yes. Just for the NF2, it's for NF2.
Regarding the correlation,
the B and the F, B and F are the same
number.
B and F, okay. But it's a same. I check the value very much time. Yeah, because they're a little different. Like maybe the point like after like a 4 or 5 number. Yeah, but they are the same. Yes.
I could understand that about the HMF to the peak height, because it's difficult to improve the HMF to estimation even with the help of NE data, but I don't understand why for the peak electron density there is no improvement. I don't know. Yeah.
Yeah, for this study, we just compare the NF2. Yeah, we are not compare the whole profile. Yes, we. Yeah, we only in this study we have the whole profile for digizone. We have the whole profile below the below NF2, below HF2, but we only compare with the we only compare with NF2 and HF2.
Maybe it's related to the size of sampling number. Something,
yeah, because
I don't. Yeah,
it's hard to gather data because you can see this one. Okay, maybe because
okay.
there are only we only choose the A station because we use the menu square. So the data is a little expensive.
Okay,
Yeah.
I see.
And
I see. Maybe
so
you
we
could.
only choose like 2 months. Yeah, because if you can also use like that has auto scale data. You can get it from the website, get online, but some profile they may has a problem. So we ask for Lowell to help us to do the manuscript. Yes. So the data, we do not have not much data to do. Only 2 months. The period is only 2 months. Yes.
I understand. Thank you.
Thank you.
Thank you very much. Yeah.
Thank you very much, Haisha. Now we have a question from Lin. Let me see, Lin Qingho.
Okay, yeah. Okay, so good morning, Professor. So I have one question is that because we know the ionosphere, the structure will be changed during the night. So
yes,
it's a E layer might be disappear and the F layer will be shrinking from the 2 become a 1 layer. So that's just because the solar radiations, their energy provides is not enough for the ionosphere. So that's why structure will be changed. So my question is because in some time when the Earth they are rotated into the day that side. Sometime when on the solar eclipse, so the moon will be block the sunlight into the Earth. So in this time it's day, but still there will be also one dark area. The shadow of the moon will be cover the Earth. So what happened of this ionosphere during this solar eclipse? So will their structure appear any change? So that is my question. Thank you.
we try to do is we try to do the event in 2017 because there's a lot of ground-based data, but unfortunately there has no much data in the 2017 event for radio occultation. But we do like if you do 1 hour resolution, then we can only see the we can only see the TC depression, the density depression. So we try to use like a 5 minutes, like we increase the time resolution for 5 minutes, and we assimilate like I think it's a 3,000 ground-based receiver, and so in that one, like the westward shift very low because the time resolution become 5 minutes. So each time stay like a shift very small, but we assimilate a lot of data, so we can still see the depression and also see the vertical variation. But I'm not showing in this. I'm not showing this one. So maybe in the future I can. Yeah, we are writing a paper now, so maybe in the future, or maybe you can contact me. So there's a maybe, or maybe, yeah.
So is there any difference between a total solar eclipse and an annular solar eclipse? Because in this 2 types solar eclipse inside the stream of the sunlight into the Earth in the moon shadow is different.
I think I'm not doing this very much. I just remember like I think 100% total electron total solar eclipse induce a lot than maybe I think if just like a 99 or 95, the depression is not like a total eclipse, like they are depression a lot. Yeah. But I have no figure can show to you for now.
Okay, thank you, Professor.
Thank you.
Thank you very much. Very good questions we met in today. So now Olu Yimo has a question. Please go ahead.
Good afternoon or is it evening? Good day. So I just have a question because I am working on something relating to S4 index. So this kind of data is new to me. So, but what I've discovered is that I've been trying to check the data. So I don't really get the altitude profile parameter from the ones I've been coming across. So I really don't know, is it that I have to check elsewhere for the altitude parameter? So what I just have is, they'll show the series, that's the time, and they will also give the SNR either from the L1 or the L2 GPS receiver. So I want to know if I'm working in something related to that, how do I get all the parameters that are involved?
Could you say again? Sorry. Could you say again? So, like, if you use like S4, you can. I think the Cosmic they has provided SNR data. I think for radio occultation, but I'm not familiar with that. I'm not do the S4 too much, but
Okay.
you can go to a CDAC or TSCD to download the SNR data. I think they have the SNR, the S4 profile data. I think that maybe POD data they include the SNR data. So maybe you can try.
Okay. Thank you.
Thank you.
Very good questions we are having today. Then we don't have more questions right now. If somebody wants to make a comment or something, we will go with the summary and a few words of Professor IP Wing. Any additional comments?
No, I mean, thank you so much, Dr. Lin and also Andres on moderating this talk. And I think that we also have some good questions. And then we hope that Andres will be given the next talk on October 17th. And hopefully all of you will return and also invite your colleagues to join this seminar. I think this is a good way to exchange information, across continents.
I would like to give some links for the attendants. Maybe they can just research some information if I'm allowed to share a little bit. It's okay. Can you see my screen?
Oh, maybe I start.
It's possible.
Are you showing are you sharing your screen? Are you sharing the screen? We haven't seen anything yet.
Yeah, I think AJ wants to share the content. Maybe you have to give me some permission or something. Well, anyway, I can leave it in the comments. It's okay. So I'm leaving in the comments the links for the AOGS Regional Advisory Committee, which you can access and see next event. Then I also would like to give the website of the Geodetic Space Weather Research of the IAG, in which I'm carrying one group. Also, you will find there information about space weather as well. And also, I would like to share the link of the Young Earth Scientist community, which is for young early careers for sharing knowledge. You can register there and go to the community. And well, that's all for today. Thank you very much. Okay, thank you everybody again. Thank you. Thank you. And have a nice evening or good morning. Okay, bye-bye. Thanks for attending. Have a nice day, a nice evening all around the world. Bye-bye.
Bye.
Thank you. Bye.
林博士，谢谢你啊。
谢谢。